hi everybody. Can you all hear me?
Yes.
Okay, excellent. So welcome to lecture 7. And I think as usual, I'll go right into it. I'll start with a little reminder of what we did last time. And then, well, we'll continue with a short discussion of some of the implications. And finally, well, we'll go on to basically a new part of the course. But let me just see how I exactly. It's better like this. Okay, so right. So as a brief reminder, so actually the thing that we will make most use of for this next part, where we'll actually try to derive nonlinear gravity and then quantize it, are the soft theorems. But anyway, last time we talked about two different things, but I'll go in chronological order. So, well, we finished off the discussion that we had previously begun of soft theorems. And of course, for us, this meant, what did this mean? Well, it meant that we looked at some process with some arbitrary scattering from an initial state alpha to some final state beta, and we compared it to a very related process, which is the scattering of the initial state alpha to a final state beta, where I added either a single graviton or a single photon, depending on which interactions or which theories we would like to talk about. And by looking at the soft limit, meaning where the momentum of this additional quantum here was taken to go to 0, we found two very interesting conclusions. We arrived at two very interesting conclusions. The first was that if we added an additional quantum of spin 1, a photon, then the consistency of these amplitudes or S-matrix elements required that the charges be globally conserved, meaning that the charges of all the ingoing particles that can couple to a photon had to sum to the same as the charges of all the outgoing particles, in the sense that the charge means they can couple to a photon. And actually, a seemingly simple generalization of this, namely by adding just another index going to the graviton, actually made the equivalent constraint a lot more well, constraining. And in fact, what we found was that now we got a vector constraint, and this, in order to solve this in a sensible manner, we actually found that the spin 2 had to couple in exactly the same way to each of the ingoing particles and each of the outgoing particles, which of course could, according to assumptions, be any particles. Well, we only looked at spinless ones, but I told you that their analysis can be done also with spin. And anyway, the gravitational coupling had to be the same for each of them. And this is what is the manifestation of what we would call the equivalence principle when we treat gravity as the exchange of a massless spin 2 quantum. And so this equivalence principle follows from the requirements that we have put into the theory so far. Okay, and so now our goal will be to use, in particular, the spin 2, all of the constraints, including the equivalence principle, for spin 2 to build up essentially what we know to be gravity, so the nonlinear theory, both in the classical case, that will be mostly what will keep us busy today. And then we will go on and talk about quantum effects in this theory. Okay, so however, before we get there, I would like to just finish the discussion on the second part of last lecture, which was the Weinberg-Witten theorem. And why? Well, I discussed this because it was actually sort of the right time to discuss it. We had all the ingredients at our hands, and it will become very useful at a later stage in the course. It would be very good to have this at our hands. So just let me remind you very briefly of the logic that we used in order to arrive at the Weinberg-Witten theorem. Well, essentially, this followed again from requirements of unitarity and Lorentz invariance. And the way that we derived it is actually very simple, given that the theorem is very powerful. Well, maybe that's the reason, in fact. But at any rate, all we needed to do is we needed to understand, first of all, what are these objects p plus or minus h. So these were the elements of Hilbert space that correspond to the representation, unitary irreducible rotation of spin +1 or +2. And we looked at matrix elements of a conserved current J mu or T mu nu between those states. And basically, we argued that they had to be non-zero just by using Lorentz invariant and the definition of charges. But we found that we could actually use a consistency equation for how these things transform under Lorentz to get a constraint which told us that they actually had to be zero for certain values of this helicity H. And in particular, it had to be any helicity greater than 1/2 if we look at the matrix element of J mu, and any helicity greater than 1 if we looked at the matrix elements of T mu nu. And so to avoid this obvious contradiction, namely that they have to be at the same time zero and non-zero and zero, one must exclude massless particles for spins or helicities greater than 1/2 from the spectrum if one considers the case of conserved current J mu with one index, and one has to eliminate particles with helicities J greater than 1 massless if one considers matrix elements of T mu nu from the spectrum. And so one of the main motivations, so I'd like to now immediately launch into a discussion of some of the consequences for which we did not have time last time around. So, so some comments on this. So the question is, of course, well, what is it good for? Okay, so maybe the first question we'll talk about is, what is it good for? And one of the contexts in which it comes up quite frequently, and also which I actually used to motivate it, is that this Weinberg-Witten theorem, it rules out the idea of emergent or composite gravitons under certain conditions. So Weinberg-Witten rules out, let's say, certain constructions of emergent, or one might say composite gravity or gravitons. And so what's the point here? So let's see, the idea behind this, behind such constructions is that, well, we acknowledge, we take on board that there are difficulties in defining a UV complete quantum theory of the graviton, which, by the way, will occupy us for the next few lectures to really make such statements precise. But anyway, you've probably all heard about it. But so there is some problem with the graviton as we know it in the UV. Okay, so the idea to get around this is, well, let's just say that the graviton is a composite. Okay, so this means that at some energy, okay, so at some energy, it simply dissociates. So we find out that if we go to high enough energies, there is no longer actually a graviton itself, and then the UV theory is just, if you want, is just given by some standard renormalizable Lorentz invariant QFT. So is some standard, meaning not containing a graviton, Lorentz invariant renormalizable quantum field theory. And wouldn't that be great? Because that would be a very elegant way of getting around the UV problems of the graviton. However, the problem is that it just won't work for the reasons, well, because it is in trouble with this Weinberg-Witten theorem. So the problem is that it won't work, at least as I stated here. And the reason is obviously the following. The reason is that such a theory, okay, so we have Lorentz invariance, and we have a conserved T mu nu. Okay, this is just, if you want, implicit in this part of the sentence, standard Lorentz invariant normalizable quantum field theory. And so, well, that means that in the spectrum there cannot be a massless spin 2 excitation. And we don't care whether it's fundamental or composite or anything. This, you know, the theorem makes no adjustment for that. So this doesn't work. And so in that sense, this really a very attractive idea of emergent gravity and getting around the UV problems of the graviton that way is just not allowed. Now, good. So that was just an illustration of one of the powerful applications. Now, the second bit that I want to say is, okay, what is it good for? Well, what is it not good for? So what the Weinberg-Witten theorem is not good for. Or rather, what are some ways that we can get around this theorem in familiar circumstances? Aranaba, please.
Can you just clarify the last point once more? So we said that that theory contains a graviton at low energies, right? Mm-hmm. Even though it is composite. So it can, I didn't understand that point, that it won't work because it has it is Lorentz invariant and conserved T mu nu.
Well, if the UV theory is some standard Lorentz invariant renormalizable quantum field theory, so let's say you could come up with some version of, let's say, quantum electrodynamics. Mm-hmm. Okay, that obviously has its Lorentz invariant and has a conserved T mu nu.
Okay,
just has its T mu nu. But let's say you modify the theory in such a way that you find, well, you want to modify the theory in such a way that it contains a composite particle that has the quantum numbers of the graviton.
Okay.
That won't work because we know that we're not allowed to have such a particle in the spectrum simply by the constraints of the Weinberg-Witten theorem. So you shouldn't even try and look for such a theory.
Okay, but doesn't this rule out graviton altogether?
Well, that's what is it not good for?
Okay,
it's a good question, but that's what we're discussing now. But we're going to get there in 3 steps, I think.
Okay.
Okay.
Thanks.
Sorry, what is going on here? 1 second. Did someone send me a message? No. Okay, I think somebody just joined or something. Maybe that was it. I got some notification that was half hidden. All right, so good. So we'll start. What is it not good for? So hopefully it doesn't rule out gravity as we know it, general relativity. But let's go step by step. So A. So you could have been less ambitious and you could have asked, what about the photon? So E&M, quantum electrodynamics itself. This obviously has a massless spin 1. But that's allowed for a much simpler reason because the graviton, the photon doesn't carry charge itself. Okay, so that's okay. Good. So electromagnetism is allowed to exist, but in a sort of obvious way, and that already illustrates where we're going to go with the graviton, because the graviton is charged in the sense of, you know, it carries energy momentum, which was essentially the charge in the gravity case. But okay, electromagnetism is allowed to exist, but we can actually come up with a version of electromagnetism where the photon, as it were, is charged. So massless Yang-Mills theory, right? So let's say the gluon, for example, is charged, okay? So what's going on here? Well, the problem here is actually somewhat subtle. It sort of seems like a technical thing. And I believe that I put a question on that on the the second problem set, okay? The point is that it doesn't have a current J mu, which is at the same time conserved and gauge invariant. So there's, in other words, no good definition of the Lorentz invariant current. So it evades the Weinberg-Witten theorem because of this, that you can't, so you push on one and you try to fix gauge invariance, then you destroy Lorentz invariance, and the other way around. And so that's actually, so maybe I'll say see example sheet, see example. And that's actually the answer also to Arunaba's question, because GR also has, so GR obviously has the massless spin 2, but it does not have a gauge invariant Lorentz covariant T mu nu either. No gauge invariant Lorentz covariant conserved T mu nu. And that is the subject, to look at this, is the subject of one of the exercises. Sorry, I cannot seem to write at the bottom of the page here, it just doesn't take it. So conserved T, but I mean, of course, T mu nu. And that's one part of the exercise set. So I don't want to go into the detail of some calculation here, but you will see precisely what the problems are there on the problem set. So it doesn't rule out those things, okay? And that's good, of course, because otherwise, well, as Arunaba already pointed out, we should be worried. Let me shift this a little bit off the page. T mu nu. T mu nu. Okay. And so then finally, the last comment I want to make is number 3, which is, does the Weinberg-Witten theorem kill all hopes of emergent gravity? And the answer is no. So there are, of course, 2 ways of getting around it, okay? We're going to spend quite a lot of time on one of them. So the first one, which we're not going to spend any time on, is that you could actually say, you start with a non-Lorentz invariant, I always call this substrate. Okay, what do I mean by this? Of course, I mean that there is this UV well-defined quantum field theory from which there emerges the graviton degree of freedom. That's what I call a substrate. Okay, but we're not going to spend any time on this, although it would be interesting. But the second way of getting around it is something that we're going to spend, well, basically half the course on, and this is an example of emergent gravity which evades Weinberg-Witten. It's called holography. Holography or ADS-CFT. And the way that holography gets around it is that the emergent gravitational physics does not take place in the same arena. In fact, what you have is you have an emergent extra dimension as well as an emergent curved geometry, namely that of Andy de Sitter space, this ADS. And so the Weinberg-Witten theorem does not constrain this kind of emergence, but we will get to the meaning of all these words when we go to the ADS-CFT chapter. But what I want to point out is that holography, one of the reasons also why it is intellectually very satisfying and very interesting is that it addresses precisely the impossibility of getting a emergent gravitational physics from an underlying Lorentz invariant theory that doesn't contain gravity, and it circumnavigates the constraints of the Weinberg-Witten theorem, I think, in an extremely fascinating way. Okay, but this is, of course, for later. Okay, this is not going to be our immediate next topic, but we're slowly moving there. Okay, well, excellent. So this is all I wanted to say. Basically, this really concludes now the part of the course where we talk about constraints, okay? And what we're going to do next, starting in a minute or so, is we're going to use now these constraints to systematically develop the consistent theories of spin-2 massless quanta. So maybe it's a good time to ask if there are any questions. I don't see all of your hands, so it's probably best if you have questions, if you just speak. Okay, so it seems like there aren't any questions, so let me move on now to, if you will, the next chapter. And the title of this chapter is directly Gravity as an effective field theory. Okay. So let me say we have like a set of, so we have developed a set of powerful ideas and constraints and obviously I'm reiterating those things, but it's worthwhile to list them now. So gravity we want to think of as a quantum field theory of massless spin-2. Okay. So this was the thing that I said at in the very first lecture. Instead of deriving gravity from a, let's say, beautiful geometric principle as it was done first by Einstein and Hilbert, we're actually saying gravity is just the exchange of a massless spin-2 degree of freedom, and we would like to ideally arrive at this this beautiful geometrical structure a posteriori. Okay. And so this QFT, of course, is equipped with a unitary causal, local, and Lorentz invariant S matrix. Okay. Then what we found out by studying, therefore, the unitary irreps for spin-2 of Poincaré. Okay, so in particular for spin-2, what did we find out? Well, we found out two things. Well, we found firstly that the field operator that realizes them had to be equivalent to the field operator plus some shift which is linearized diffeomorphism invariance. Okay, and so therefore we want to build up things from invariance, such as so invariance, okay, such as this R mu nu rho sigma, which was essentially the simplest invariant quantity that we could find, and that is in some sense the direct analog of the Faraday tensor for the photon. Okay, and notice that this is quadratic in the H field, HDH, and of course we have couplings to matter fields via this T mu nu, which has to be conserved, H mu nu, T mu nu. This, of course, being the direct analog of the A mu, J mu coupling, which you have for the photon. And then, secondly, we have this soft graviton theorems. We have soft gravitons. And so the soft graviton theorems, they tell us that if we do undertake such a coupling, then it better obey the equivalence principle. Okay, and so those are the principles which we have deduced, and which better, all of the theories that we want to construct here, they better respect these principles. Okay, excellent. And so the goal, the immediate goal now is to build such theories. Okay. Now we're going to, our goal is to build such theories. Okay, and the tool that we're going to use, and that will lead us on some excursion, which basically will be second part of today and most part of next week, next lecture. So the tool is effective field theory. And this will be developed. So I'm going to systematically develop this idea as well. I realize that some of you probably know this extremely well, but I'm going to develop it, first of all, because I'm not sure that everybody knows it extremely well, but secondly, also, I'm actually going to develop it essentially already on the example of spin 2. I will first give you like a little illustration that uses a simpler context, but I'm going to develop it mostly on the example of spin 2. Okay, and the immediate advantage by using an effective field theory is, so I'm just going to state it now, but that we can use weakly coupled Lagrangian methods. Okay, and we will justify this statement actually maybe later today, or as I said, in the next lecture. Okay, why, if you work in this EFT regime, that immediately implies that you can use weakly coupled Lagrangians. And then, of course, we also need to convince ourselves that for gravity in particular, there is a good EFT regime. So it's actually a good idea to even try to do this. In fact, it is an extremely good idea, but we're not there yet to really argue why and how it works. Okay, but so so this effective field theory, of course, also carries with it the implication that we're going to look at quantum effects, which is the case. But before we go into the quantum realm, I would like to first show you how to get actually to the nonlinear Einstein theory at the classical level. And so that's what I would like to spend some time with next. So that's, of course, that is part of implementing these ideas here, okay? If you want step one. So let's do this now. Einstein-Hilbert. Now the ideas here, I think, are really rather simple, okay? Unfortunately, the calculations are not. So first of all, that means that I really don't have the time to do a significant amount of these calculations here on the blackboard, as it were, the virtual blackboard, although I will try to give you all the ideas. But I have put a detailed question on the second problem set. Okay. What I want to say, though, to you is that I am aware that this is not an easy question in terms of the amount of calculation that is involved. So please don't get discouraged. Okay. I just wanted to give you the opportunity to go through these things in detail, and I encourage you to do this using some kind of computer algebra if you can, because doing it by hand, I don't think I would have the patience to do this by hand. Okay. But anyway, so what we're going to do now is going to be going through the steps that are also outlined again in problem set 2, and I'm going to give you the main ideas that you need to actually address each of those steps. So first of all, let us start now by building the appropriate Lagrangian for the free graviton, again, that satisfies our principles. And I'm allowing myself now to work with Lagrangian because we're going to work within this EFT, and within this EFT, we can actually start making progress from Lagrangians. So let's start with free gravitons. So that means that we now seek an action that has the following properties. Well, it is obviously quadratic in the graviton field H, so I don't always write the indices H. It has a two-derivative kinetic term. And it is obviously invariant under this change in H, delta H mu nu, which is equal to the symmetrized derivative on some arbitrary vector function xi nu. Okay, and so then by dimensional reasons, simply by dimensional reasons, we're looking for something where S will go like some dimensionful parameter mass squared, which people like to call the Planck mass, times d4x h d2h. And h d2h, well, what do I actually mean when I write this? Well, it's just, it's quadratic in H, has a two-derivative kinetic term. So this is just dimensional counting, so alpha is just some number. And I'm saying is approximately equal to, because we have to think about index contractions, okay? This is extremely symbolic. So we need to figure out what are the index contractions that actually give us this for a spin 2 field rather than just symbolic for H. Well, so the index contractions, the correct index contractions are actually where all the interest lies. So index contractions will allow implementation of the invariance principles. Okay, so well, we'll just start with what you can write. Well, of course, a good first guess is the following. The action S now is equal to this parameter alpha, which we're going to fix, times the Planck mass squared times d4x times, well, for example, well, not for example, one good thing is it better be rho mu nu, r mu nu rho sigma here, where the 1 just means the linearized one that we wrote down. Okay, so this thing is already invariant. Okay. So then here we just look at how we can write the indices. So we have to have 4 indices, mu rho, and then we could have h nu sigma. But then of course h also can have a trace. So there's some arbitrary coefficient times the trace, h, and then we should better make up the indices using the h mu rho, h mu sigma tensors. Okay. And so what we want to do is we want to say choose A to satisfy invariance principles. Okay, of course, and I hope you will go through this in the problem set. The proper way of doing it would be to just write down all polynomials that you can in that are quadratic in H and that contain at most 2 derivatives. Okay, but sorry, that contain at most 1 derivative, because we're in the action, so it gives a 2 derivative equation of motion. But as I said, I have to do some shortcuts because otherwise the algebra gets a little bit overwhelming, and you have the opportunity to fill in all those details on the problem set. But let me just tell you now, once you've whittled it down to this, so let's assume we've whittled it down to this, or we just call it a good first guess, okay? Then what we need to do is now, of course, we should choose A such that the variation, so we want that the variation under this infinitesimal linearized diffeomorphism, L, is at most a total derivative. Okay? Sorry. Right. Is at most a total derivative. So, well, it's easy to write down delta L. So delta L, so obviously I want to call the integrand here, presumably including the alpha and Planck squared, I want to call this L. Okay, so this thing here, let's call it L for now. So then delta L, well, it's just eta mu rho, and then for the H, we can put the derivative here, d nu psi sigma. Okay, we can forget about the explicitly writing the symmetrization because it contracts into symmetric indices already. Then we have A times the divergence of xi, d lambda xi lambda, times eta mu rho eta nu sigma into the linearized Riemann mu nu rho sigma. Okay, and then of course you can whittle this down a bit. But so the first thing is that this eta mu rho contracting into the mu rho index here. This is of course what we call the linearized Ricci. So this is, if you want, this is d nu c sigma times r1 nu sigma. Okay, plus A times the divergence psi lambda r1, which is the Ricci scalar. Okay, and then we can write this out explicitly. You see now already, I mean, I'm really trying to eliminate as many details as I can, or skip the messy parts, but we're gonna just write this out explicitly now. So the linearized Ricci and the linearized Ricci scalar and Ricci tensor give us the following expression. So this is the box, okay, the D'Alembert operator on H, plus H sigma alpha comma nu alpha. Let me just say that the notation is, okay, notation is, for example, H comma mu means d mu of H of the let's say the trace, and equally, of course, if I had indices, I could say H alpha beta comma mu This is just d mu on h alpha beta, etc. Okay, so these are just ordinary derivatives, the commas. Okay, so this guy plus h nu alpha comma alpha sigma, so I'm summing over the index alpha, minus, in fact, the trace h comma nu sigma. Okay, this is the first term. And then from the second term, we get plus a d lambda xi lambda times h mu alpha, so the two derivatives summed minus box on the trace h. Okay, well, that's so far so good. So one simple way of fixing this is, so we have terms where you have h as a two-index tensor, and then you have terms, if you stare at this, which involve only the trace. So we have this, the derivative, the new sigma derivative of the trace h, okay, and we have also a trace term here, which is the D'Alembert operator, oops, the D'Alembert operator acting on the trace, okay, and both of them are proportional to some term involving the parameter xi. And so one way of fixing what A is to just look at the terms involving the trace. So let's do that, because in particular, those have to work out. So let's look at only trace terms. Look at trace terms, meaning involving the field H, not H mu nu or anything like that. Well, what I can do is I can write, so I get minus 1/2 d nu xi sigma d nu d sigma h lambda lambda. I guess I'm writing out the indices explicitly here. So this is obviously just a way of writing the trace. And here we have just the nu and the sigma derivative acting on the trace. Minus a, and then we have d mu xi mu times, well, why, yeah, I think I'm writing out the indices explicitly here because it makes the next step more obvious. H lambda lambda. Okay, those are the two trace terms which I had actually already pointed out. Now, the point is that I can write these as d alpha v alpha. So this is some total derivative plus 1/2 plus a times d alpha d lambda xi lambda d alpha h, where v alpha is actually equal to minus 1/2 d nu psi alpha d nu h plus an a term. What can I say? Actually, I can say I redid this calculation last night, and I found that in my notes that I'm lecturing from now, I had actually omitted to write this a term, but very intelligently I have written the a term on my iPad, which I'm using now. So I'm going to supply the a term after the break. But so there is an additional a term here, okay? But anyway, I mean, the point is that this bit here, so this bit is correct. So what we have is we have a total derivative, okay, plus something that is not a total derivative, but that is equal to, proportional to 1/2 plus a. And so of course, we conclude therefore that this is a total derivative if a is equal to minus 1/2, okay? And actually with this choice, the other terms are also invariant, meaning the total variation is a total derivative, okay, which is, of course, as I said, it's one of these details, tedious, which I am delegating to the second problem set. So now this is actually a good place to end, because So after the dust settles, we now have almost the quadratic action. Okay, so after the dust settles, we have actually now the following quadratic action. We have the graviton quadratic action, which is still equal to our alpha mp squared, and then there's an overall factor of 1/2 that you can put out, and then you have d4x, and now we have a bunch of terms, but those terms are actually not so bad. We get h mu nu box h mu nu, so the sort of standard quadratic term that you have for a field. Then of course we also have the trace, which has the same minus h dh, and then there are some correction terms which just come from the fact that we have, you know, interesting index structure, and they can be written as twice times the trace of h times d mu nu h mu nu minus, and then there's one more term, h nu sigma d nu and d mu h mu sigma. And okay, the last thing I will say, so okay, I will put a box around this because this is very important. Okay, what is this, however? Well, with some hindsight, I can just tell you that what this is precisely the quadratic part of the action S Einstein-Hilbert, which is equal to 1/16 pi g times minus g times the Ricci tensor. And the quadratic part where I'm saying that the metric g mu nu, I can't write down here, the iPad won't let me. So where basically h mu nu is eta mu nu plus, sorry, g mu nu, the metric is h mu nu g mu nu, gosh, the metric g mu nu that I am putting in here to compute both the determinant and the Ricci scalar is equal to the flat metric eta plus h, and I keep only quadratic terms. Of course, we need to still choose alpha to make this work, which we will do after the break. But the point is that we have derived the quadratic Einstein action now without ever having to invoke these geometric principles that usually lead to them. Yes, Manos. So I'm gonna stop here. Please, questions now, and then we'll return after the break. So Manos, for example, has a question.
Yes, I have a question about the variation of the Lagrangian, where you computed that.
Yeah.
Because is there also a term where the variation hits the Riemann tensor?
But that's invariant under the, right? That was the point. That's already gauge invariant.
Why is that? Oh, just
we constructed it to be so.
I see.
Right. I mean, sorry.
How does that work? Just if you hit it, it just cancels all the.
Yes, and I mean I tried to say it like that in the corresponding lecture, but you see in the F mu nu case, it's very easy to see because you have the anti-symmetrized derivative, and so the d mu lambda type things cancel out.
Yeah.
And because you have a slightly more complicated d mu lambda version, this symmetrized d mu xi nu, you have to have more indices to get the cancellation between the different terms. But that's precisely how I actually motivated the linearized Riemann tensor in the first place.
Okay, yeah, I remember. Thanks.
Any other questions? Also, it'd be nice to have birds in the background as well. Okay, no questions, no birds. So then I'll see you in 10 minutes at 11:15 and on the other link. Okay, take care. Bye bye. Okay, I'm just gonna carry on. But so these are some of the notes I wrote last night. So I just wanted to point out that, okay, if we look at the if we look at the terms that are just involve the trace and derivatives on the trace, okay? So then the point is, of course, if we try to integrate them by parts to isolate the total derivative term, then we find both a term from here, which is the one I wrote. So the one here in parentheses is what I called V, and then there is another term that comes from partial from integrating by parts on the A, and that's, so here let's look at this equal sign. So that's this thing. So it's basically A times the covariant divergence of Xi times d sigma H. Okay, so there's a second term, but okay, that's just as a for completeness. So wonderful. Let's go on. So oh, actually, yes, sorry. The next thing also I can just tell you. So the point is that we write down, you know, the explicit calculation would be that we write down this action here with the coefficient -1/2. Then we write out the actual expression for the linearized Riemann tensor. We do all the contractions and we find precisely what I have in the notes. Okay, so this is some kernel, but then in particular, in order to fix what this coefficient alpha is, the way to fix this coefficient alpha, this is of course now in some sense convention, right? Because what I just introduced the Planck mass in some sense because there had to be a dimensionful constant of dimension and mass, okay, as mass squared. But we want to compare this to what we get from the Einstein-Hilbert action if I expand around flat space to quadratic order in H, and if I do this, okay, so I actually put in the linearized Riemann tensor, then I get some equation which tells me actually that alpha in the end is going to be the quotient of 8 pi gn over 32 pi gm, which is equal to -1/4. Okay, so let me just maybe add that to the very last page here. Okay, fixing alpha to coincide with usual definition, m Planck to the -2 is equal to 8 pi g Newton. Okay, one finds that alpha is equal to -1/4. But as you saw, again, this is a relatively simple calculation, which is also on the problem set. Excellent. So that's just some, you know, if you want convention consistency with the usual convention, so that what we actually called m Planck squared is what everybody calls m Planck squared.
So can you please show the expression of alpha once more?
Alpha.
Yeah.
It's -1/4, but yes.
Oh, it was just -1. Oh.
Yeah.
Oh,
Yeah. No, sorry, but I obviously removed it too quickly. But as usual, I mean, don't worry in the sense that I'm putting these notes immediately on the Moodle, or almost immediately on Moodle after we're done with the lecture. Okay, great. So now comes something that I find really is quite amazing about gravity. So now we've calculated the linear part, okay, and we've somehow we've discovered that our building up the theory from representations and so on and so forth, Lorentz invariance, gave us exactly linearized Einstein-Hilbert gravity around flat space. But of course, there's much more to GR than the linear theory. What is amazing is that actually even the nonlinear terms can be derived. And so we do this now by adding interactions. So we've already said that by diffeomorphism invariance, H mu nu must couple to a conserved stress tensor. Energy momentum tensor. So S should be equal to our quadratic part plus a coupling d4x H mu nu T mu nu for some conserved stress tensor T mu nu. Now, let's use a trick. Okay, so in particular, of course, we know the graviton itself, G itself, has a stress tensor. Okay, this is this physical principle that that gravity reacts to everything that carries energy, including the graviton itself, which obviously carries energy. So we can calculate what this stress tensor is. So one simple way of calculating it, calculate this from the quadratic part of the graviton action. So I find the simplest is by coupling to an auxiliary metric. Auxiliary metric. So again, I always say that, but this is explained, and then you're invited to do this in the problem set. But here the principle really is very simple. You just introduce a metric, let's call it m mu nu, and all the index contractions that you find in the quadratic action, you now do it not using eta mu nu, but this m mu nu, and then of course the variation with respect to m in the usual way defines a stress energy tensor, and at the end you vary with respect to m, and then you set m is equal to eta, and that gives you the stress tensor. And that stress tensor looks like this. Let's call it tau mu nu. Okay, this is going to be equal to minus a quarter h alpha beta times d mu d nu h alpha beta plus some other terms, which is not important. What is important now is that this thing is actually order of h d2h. Okay, so it's quadratic in the graviton, and this is why I call this tau 2. Okay, so what does this mean? Well, so there is a quadratic term in the graviton, and now if we look at our action, okay, this wonderful thing happens. We have an action which is quadratic in the graviton, and now we couple it to its own stress tensor, which we just derived. Now we have something that is quadratic in the graviton plus one factor of the graviton, so we have suddenly a cubic term in the graviton. Okay, so thus we construct SH3. So this is now an action which is cubic in the graviton, which is equal to SH2 plus d4x h mu nu quadratic part t mu nu, okay, which, well, sort of semi-explicitly gives us the quadratic part plus, okay, d4x h mu nu, well, minus 1/4 h alpha beta d mu h alpha beta plus these other terms. Okay, let me copy paste to take it to the other page. Copy. Oh, view single page. Here. Okay. So now the point is, the important point is the following, is namely that, of course, this thing here now is order h cubed. It's cubic in our graviton. And so we can say that physically what happened is we just constructed a 3 graviton vertex. Namely, well, something of this kind, which is, of course, equal to our h mu nu T2 mu nu. Okay. So what's sort of amazing, the amazing bit is that this coincides with Einstein-Hilbert expanded around flat space to order 3. Oops. Order 3. Yes, Arunabha has a question, yeah?
I kind of missed the point of how did we construct the tau mu nu 2?
Well, you go to the quadratic part of the action, and you introduce what I think people like to call a fiducial metric. So you do all the index contractions in the quadratic part of the action. I haven't written it here. And you do all the index contractions in the quadratic part of the action using this pretend metric. But now, of course, you can consider infinitesimal variations of this pretend metric, and you know, of course, that d s quadratic by d pretend metric mu nu, where I'm evaluating m mu nu at flat space, this defines t mu nu indices down. Sorry, and I can be more specific. I mean, this defines here my T2 mu nu, exactly the one I want, because I start with this here, okay? And as I said, you're invited then to show that you get a specific expression, which is this plus, I think, just one other term, okay? It's not so different from, I mean, it's not so different from doing it for Maxwell theory, right? Just that the index contractions are a little bit more annoying. And then you see we do this coupling, and it's now of order h cubed, okay? But it's not just some arbitrary order h cubed. It's precisely what you get from Einstein-Hilbert if you keep all terms up to order graviton cubed, okay? But now you see what we're going to do. Okay, let me make this to be some remark. This is the our definition of tau mu nu 2. Okay, yeah, thanks for that question. Okay, but you see, we don't have to stop there, right? Because what we can do is we can now construct iteratively. So we do the next. We now construct in exactly the same way T mu nu 3 from, oops, sorry, from S3. Okay, I think I could set that on the previous page, but of course this thing, we can call this S3. what do we find? Well, we construct this guy and write, well, obviously we're going to write S4 which is equal to SH3, I guess I should have called this SH4, SH3 plus D4X H mu nu T 3 mu nu, okay? And now this guy is of order H to the power 4. So there is now 4 gravitons. And so what we've done is we've constructed a 4 graviton vertex, which is the vertex H mu nu tau 3 mu nu. And guess what we get? Well, it's the 4 graviton vertex. Of Einstein-Hilbert expanded to order H to the power 4. Wow, I mean, I think this is quite amazing. Now, of course, we can just generalize, right? As physicists, we've checked it for 2 gravitons, 3 gravitons, 4 gravitons, so it's obviously true for an arbitrary number of gravitons. So this gives us an iterative procedure to construct uniquely, I guess, vertices with an arbitrary number of gravitons. One sec, Arunabha, let me just and all of them have but and only ever 2 derivatives. Okay, this is what I wanted to say. Only ever 2 derivatives, okay? And amazingly, actually, one can show, that the infinite sum reproduces the nonlinear Einstein-Hilbert theory. Einstein-Hilbert. Okay, let me just say 2 more things here. Well, actually, just one more thing before I give the floor to Arunabha, which is something that I learned. So first of all, there's a paper by Deser, which I'm actually going to put, Stanley Deser, which I'm going to put into the Moodle, who shows this explicitly, and he actually does it in a way that is much more elegant than what I am showing you here. I gave you the pedestrian way of doing it because I wanted to basically just give you the simple ideas. But Deser basically uses a Palatini type formalism and shows once and for all that indeed the statement that I'm making here is correct, that you get Einstein this way and that you don't need to just say 1, 2, 3, many. You can actually show it. But you have to do some formalism and you have to add some formalism in order to show this. So I'm going to put that paper by Deser in the Moodle folder. And the other thing that I learned from this paper by Deser, which I wanted to say, which is kind of fun, is that this has been known for quite a long time. One of the people who pointed this out apparently at one of the Rochester conferences was Richard Feynman, but in fact it predates even Feynman. So the first notion that the first mention of this was Papapetru in the 40s, and Kreishnan, who is actually very famous for having essentially revolutionized the study of turbulence. But before he did that, he was actually Einstein's assistant in Princeton, and Krishnan also in the late 40s or something also pointed this out. So it's an old idea, but yeah, it's still very nice to show it here. Okay, so Arunabha, please.
Yeah, I wanted to ask something related to this. Like, how does one see that it always uniquely reproduces EH? But you said this paper shows that.
Yes. That's probably, I'll leave it there because you have to go into this Pelletini thing and so on. The point is that you can sort of show that this resummation is correct. But I will give you a perspective with hindsight that actually shows, maybe gives you a little bit an idea why this should be true. But I'm using hindsight, and of course the most interesting thing would be not to use hindsight. So, very good.
Julian, I have a question.
Mm-hmm.
What happens? Does it matter if I use some other improved form of stress tensor apart from the one that I get by taking derivative with respect to the fiducial metric?
You mean this Belli-Fonte stress tensor, for example?
Yes.
To the best of my knowledge, it does not matter.
So the difference is a total derivative term or something like that, or
yeah, it
like...
must be that all the differences can be shoved into a total derivative.
Okay.
Which is probably even the definition, right, of improving the stress tensor. But okay.
Because it is always conserved, you're saying? Yeah, maybe. Yeah. Okay. Thanks.
Adrian.
So, just a comment. So, if I understand correctly, we are saying that if we try to build a theory for a massless spin 2, which has an action that is Lorentz invariant and gauge invariant, this leads us uniquely to Einstein's full theory.
Yeah.
But I don't know if this is good or bad, because at some point I expected a departure from Einstein theory, right? Because at the end of the day,
but we have restricted to 2 derivatives, and of course there will be departures, and we will even discuss such departures.
Okay. Thanks.
Okay. So, Pranjal, are you raising your hand because you still have a question, or?
No, sorry.
Okay. Yeah, no problem. Good. So, let me go to these comments.
Can I ask a small question?
Yes, of course.
Does this stress tensor have a name?
No, not that I know. No, I don't know. Deser in this paper doesn't give it a name, for example.
But he was one of the first to compute it, except for these other people.
Yeah, I am not an expert on that history, but it seems like if Feynman had already pointed this out and Krishnan and Papapedru, they probably did calculate it. But what's nice about this Deser paper is that it really shows very clearly that the full resummation gives you Einstein-Hilbert, and he uses what I find to be a very elegant way of doing it. So I invite you to do this to order 4, actually probably realistically only to order 3 in the problem set. And because I'm approaching it in such a pedestrian way, I admit that this is quite a terrible calculation that you should do only using computer algebra. So in order to really make some all-order statement, you just need to do better than doing it but in this way, step by step. Yeah. So, but now, Pranjal, you have another question. Is this correct?
Yes.
Yeah.
Yes.
Yeah.
So at the quadratic level, I thought that there wasn't much of leeway in writing a quadratic theory, and then if I start doing the whole procedure iteratively, it looks like the only consistent theory is Einstein-Hilbert.
Yeah.
So where is the loophole here to allow?
Well, but as I already said, you get only 2 derivatives.
Okay.
Everything only has 2 derivatives, right? You can go through the construction back, but you can also just take my word for it. It's a 2 derivative theory.
Okay, thanks.
But of course, you can also have other loopholes. Like, for example, you could just say that why the graviton has a small mass. Right? We used masslessness and so on. Yeah, there are plenty of loopholes, but it is still very nice to see that given the assumptions that we make, the 2 derivative completion of this is Einstein-Hilbert.
Okay, thanks.
Okay, so...
Sorry, but then it also means that it's not possible to introduce more derivatives at higher orders independent of... So like I start with two derivative theory at quadratic order, but I never generate a higher derivative theory at higher graviton vertices.
Yeah, but it's all tree level, and so that's why I want to this next proceed to the effective field theory. Okay, and then we're going to generate all these terms, and we're going to have these kinds of discussions. But for now, okay, let me finally get to my comments. Okay, so first comment is a different perspective, which benefits from hindsight. With hindsight. Well, what is this perspective? Well, we start with the equations that we know to be true. We say R mu nu minus 1/2 R g mu nu, okay? And there is equal to, well, 8 pi g, let's have some matter there, T mu nu, okay? And then what we're going to do is we're going to split the Einstein tensor into its linear part, g mu nu 1 plus g mu nu higher. Oh, I don't think I really need to say that, but we of course call this guy the Einstein tensor g mu nu is R mu nu minus 1/2 R g mu nu. So there I said it. So this guy is the linear bit. And then we have the higher order terms. And of course, it is still equal to 8 pi g T mu nu. Okay, but now we can rewrite this. So what we see is that the linear bit, g mu nu 1, is of course equal to 8 pi g into T mu nu minus 1 upon 8 pi g times g mu nu, the higher bit. And this is precisely what we would call the full T mu nu of the graviton. Okay, so we can write minus 1 over 8 pi g mu nu higher. That should be equal to T mu nu 2 plus T mu nu 3 plus, and so on. Which is of course correct, okay, which just tells us that even in the absence of explicit meta sources, there is this T mu nu 2 plus T mu nu 3 and so on, and it just comes from basically separating out the higher order terms from what we usually call the Einstein tensor, and so we are constructing the Einstein tensor step by step in an expansion in the number of gravitons. Okay, but another nice perspective is that, of course, what we find is that this corresponds to saying that essentially we're saying that d mu T mu nu is equal to 0. Which corresponds to the statement that d mu T mu nu plus tau mu nu is equal to 0, meaning that what we're constructing iteratively here is the fact that the matter stress tensor is actually covariantly conserved, and of course covariantly conserved meaning that there is a conservation equation which involves not just the derivative of the matter stress tensor itself, but also gravitational terms, and those gravitational terms are precisely those parts that are called tau mu nu here. And so there is a perspective which basically motivates the construction of this tau mu nu stress tensor by having to ensure the covariant conservation of the matter stress tensor. So this is also a perspective that is further explained in the paper by Deser. So this is my next comment, which is 2. It's just that there is an elegant proof that the full resummation of the T mu nu I gives Einstein-Hilbert is given by Stanley Deser while using a Palatini type formalism. And this is, well, I'm going to say C Moodle. Okay, and another thing that he does is he actually points out that in a similar way, you can construct things like the non-abelian Young-Mills vertices, except that in this case, of course, you know that the series terminates in some point because there is not an infinite order vertex in Young-Mills, but there is in gravity. And so he also makes this compare and contrasting analysis, which is also pretty nice. Now the third and last comment, I think, is it the last comment? Yes. The third and last comment is the following, which is that in some sense, this settles our classical analysis. Why do I say in some sense? Because you always ask these questions, which are actually very good. But of course, we could also think about classical theories involving higher derivatives. So I haven't talked about them, and I want to talk about higher derivatives only anyway in the context of EFT. But so this settles two derivative classical theory. Sorry, I'm really not sure. I sometimes get some pop-ups here that tell me actually nothing. Did someone have a question? Did someone raise their hand? Because I don't see it.
Yes, I did.
Good. That's what it means then. Okay, very good.
Okay. Yeah,
you should just talk, guys, because I don't really see.
Okay, sorry.
Yeah. No, that's fine. Don't worry.
I was just wondering if there's a similar way to do because also the coupling to matter is nonlinear. Is there a similar way to derive this from scratch, like we did for the self-coupling?
Maybe I'm not. Maybe I don't entirely understand your question. I thought that I pointed out that yes, that it has to be coupled in such a way that the matter stress tensor is covariantly conserved.
Okay.
Okay, so so this settles two derivative classical theory. Okay, but of course, what we really want to do is, Sergio, you're still raising your hand. Okay.
I have a question also. Yeah.
May I just write what I want to write in point 3, and then I'll let you ask the question. Okay. So so the S matrix, of course, the S matrix that we've been discussing, really, we want to know about quantum type scattering events or quantum amplitudes. And then the point is that, well, we realize that this classical thing that we constructed, so we can just call it Einstein-Hilbert now. I called it here the graviton action up to n vertices. This is non-renormalizable, as we will show. Renormalizable. And so we're going to want to deal with this as an EFT. Yes, sorry. So now that's all I wanted to write on this third point. So Davide, you had a question.
Yeah, I wanted to ask you if, what is can we identify a peculiarity of this action for which the resummation is finite? Because, for example, for higher spin, this does not happen, right?
Sorry, can you say a little bit more precisely what does not happen?
That summing all the possible interaction will give you some finite action. I mean, or maybe it happens up to the the derivative order. Is this also part of my question? Because I don't know.
So sorry, just to clarify, I'm not entirely sure what you mean by finite action. I mean, I'm making no statement about convergence or anything like this, but what the statement that I'm making is that if you take the nonlinear Einstein-Hilbert and you expand it order by order in the H, let's call it a formal power series, this is what we reproduce. And so now tell me so for higher spins, you're saying that there isn't a simple term that compresses this entire series into one nonlinear expression?
Yeah, exactly. And also, yeah, up to the quadratic order, this is also a statement on the amplitudes or not?
Yes, of course, for higher spins. I mean, I think either we already had that on the first problem sheet or it's going to be on this or the next. Of course, it's much more complicated to write down consistent interactions. In fact, in many cases, you can even say that there are none. So okay. There are a huge amount of constraints on higher spins. But as far as your statement is concerned, can you show that there isn't some non-linear? No, I actually, sorry, I don't quite know what. I don't quite know how to answer the question because there are so many things that break down even at the earlier steps. Let's say it that way.
Okay.
Yeah.
Thank you.
Sure. Okay. So now the next topic is going to be EFT. So I'm going to actually take a detour now for some time. I don't know quite how many lectures it will take, but I will go over how to think of quantum field theories in terms of effective field theory. And I have now the rest of what I have prepared is basically an overview of this. I don't think I have enough time even to cover the whole overview today, but I will still remind you of some basic notions from quantum field theory, which will be useful to keep in mind in order to go on. So now comes, in some sense, a parenthetical part of this course where we talk about effective field theory, because this is the tool that we're going to use now to make further progress. Okay, so we've, in some sense, now used all these constraints, and we've made a lot of progress, I would say, on the classical theory at two derivatives of gravitons. But to go beyond that, we really now have to go into the quantum realm, and we should do so using effective field theory. And so the point is, effective field theory allows us to organize what happens in quantum field theory by energy scales. So this is my overview title. So organizing QFT by energy scales. Okay, and just to remind you, or to give you a little preview of the logic, you know, it seems a little bit disjointed now why I launch into this immediately. And the point is that we are going to just see that this nonlinear theory that we just constructed is non-renormalizable. So we seem to be in very bad shape, and in some fundamental sense we are, but that actually does not prevent us from making quantum predictions at low energies. And this works because we can basically separate what happens at high energies from what is interesting to us at low energies. And the way that the separation can be done systematically is precisely using the ideas of effective field theory. So before we go there, let me just remind you of a couple of notions. So the one notion that we want is we want to recall what is called the superficial degree of divergence of some diagram. So we have some d, which is called the superficial degree of divergence, which is d is the number of space-time dimensions, schematically, okay? Plus, well, I'm going to define these quantities just now, but let me first write them. V times delta I minus d minus delta external n. So this is schematic, but this is called the superficial degree of divergence. Okay, and the point is that we look at some diagram. I don't know. We have various external lines, and we also have internal stuff that happens, maybe with loops of various different kinds. Okay, something like this, and many more things. Okay, and so what we have is let's say n external particles. Of total dimension delta external total. So this is really a sum over all the external particles. And we have V internal vertices of dimension delta I. So we're going to do such divergence counting in full detail and with all the pain associated in the next lecture. Okay, but for now, let us just remind ourselves what you can maybe remind yourself, for example, what happened in quantum electrodynamics. What one does is one counts external electron lines, external photon lines, and then the internal vertices and so on. And you get some expression which conforms to this general expression here. Now, the point is, of course, that if I have, okay, it's probably a good thing to copy paste this to the next page. Copy paste. So the point is that if this internal dimension delta I is equal to d, okay, then the more internal vertices you add, so the more complicated this internal process gets. Okay, by adding more vertices, there is still only a finite number of divergences at each loop level. Okay, whereas if, of course, delta I is greater than d, then I can increase the superficial degree of divergence just by adding more internal structure, more like of these vertices, and so there are more and more divergences at higher and higher loop levels. Okay, and so the point is that this is what we would call a renormalizable theory. And this is what we would call a non-renormalizable theory. And of course, there is the case where delta I is less than d, so it's what's called a super renormalizable theory, but it's not so important for us now. But the point is, of course, that we can immediately identify which class we're in of theory, because it is basically determined by the mass dimension of the coupling constant. And so this is the case in gravity. And this, for example, will be the case, well, for example, will be the case in QED, okay? But more importantly, just by looking at the mass dimension of the coupling constant in gravity, we see that we are in the case where adding more and more internal vertices at higher and higher loop order gives us more and more divergent diagrams, and basically we cannot cure all the divergences by just adding a finite number of counter terms. So we are basically in the situation where this theory is non-renormalizable. But, and this is the last thing I want to say, however, but, and this is really the important point, okay, say we are interested in processes below a certain energy, let's call it E max. Okay. For example, this could be the Planck energy. Why not? Then actually, what will happen is we will establish this, of course, but some process, let's say the amplitude alpha going to beta, can actually be organized into an expansion where you have some A0, you will just see in a second why this has a 0, okay, plus a sum over n greater than 1 of E, which is the energy of our process, divided by E max to the power n into an amplitude En alpha going to beta, okay, where, and this is really important, only interactions up to a finite order in dimension contribute to AK. For some fixed K. Okay, so the point is then simply that you see, for energies below this maximum energy E, all these terms here are suppressed by powers of some small number. E over E max will be some small number for processes at low energy. And I can fix myself some accuracy. Let's say I want to know this to order E divided by E max squared. I can figure out all the terms that contribute up to a finite order in dimension expansion to the required part of the amplitude. And I can calculate it by relying only on some finite number K of higher dimension operators, okay? So that means that this is the last statement for E less than E max, okay? Can calculate to a given precision by choosing the appropriate finite set. But the important bit here is finite set of interaction terms to include. Okay, so all of the statements that I've made now, of course, well, if you remember your basic RG theory from quantum field theory, this will probably be already just old news to you, but we will rederive those statements. But in particular, we will rederive them also in such a way as in order to give us a constructive way of selecting the appropriate finite set of interaction terms that we include to calculate to some given accuracy. I'm saying accuracy because some given suppression in the energy of the process over this cutoff energy Emax. And so that will be the goal now of the next few lectures, is to, you know, put precise, let's say, mathematical meat on these statements. I mean, why does it work? I think you all understand that anyway, because you have your quantum field theory courses maybe still present in your mind. But maybe I just want to remind you how it works, why it works, and then also constructively how it works, and then applying it to gravity. Okay, I'll stop here. I've anyway gone 5 minutes over time. I apologize. And I still will open the floor to questions. Are there no questions then?